Hello everyone, good afternoon. Welcome to Circuit Analysis 1. Here is the course website currently if you log in to Canvas. And Canvas is UBC's new online content management system for courses. So this is, it's not very highly populated yet. There's no lecture or anything. This is the syllabus. This is just listing the topics loosely in the order that we'll cover them. And this is the kind of thing that you've had some familiarity with from before in your first year physics. You've seen electricity and magnetism. You've seen some basic circuits, right? And you've had some math courses that the content of which are very directly relevant to this. What I hope to be able to at least partially accomplish a little bit today and maybe in the next lecture or two is to show you, hopefully, that there isn't a whole lot in this course. This is very basic material in the sense that the amount of physics you need to know for this is very little. It's a very important piece of physics, but it's very little. And if you understand that well and you have the math skills that are prerequisites for this, in principle, we should not even have to discuss these as separate topics as far as the science of this course is concerned. Because there's basically 2-3 pieces of physics, and if you know your differential equation, well, differential equations I guess you're taking now, but we'll get there a little later. But derivatives and integrals and some basic linear algebra, you know the material. So most of this course is about putting these things together and show you how to do things with them. And a significant portion of this list that you see are really engineering. So there's little basic science that we'll cover at the beginning, and the rest is engineering methods and techniques that hopefully will help you develop insight to the point that you will be able to understand how circuits work and analyze them and eventually design circuits. And this really serves as the foundation for whoever wants to do specifically electronics later on. Now, I realize a lot of you do not want to do electronics probably, right? You're mostly in computer engineering. By show of hands, how many people would rather be a software engineer than a computer engineer? Okay, that's a big chunk, right? Now, we don't have a software engineering program, as you know, because otherwise you would be in it. We have a computer engineering program, and computers include both hardware and software. And so my computer engineering colleagues feel very strongly that computer engineers should see circuits and hardware. So that's, I guess, part of it, as part of the curriculum. I hope also to be able to show you gradually as we go through this that aside from its very concrete and specific use as a foundation for whoever wants to understand hardware, there is another aspect to circuits, and that's the fact that they're a very good case example of how systems work in general, and especially linear systems, which form a very, very big part of science and engineering. And so circuits can also be thought of as just one example, as a vehicle for understanding how to model a natural system, put it in mathematical forms, and analyze it. And so there's many things that have a great degree of similarity as far as their basic mathematics is concerned with circuits in all domains of science and engineering. And so even if you're not interested in circuits, unfortunately you have to take it for your program, I hope that the way we approach them could be useful in giving you insight that you can apply to other systems, even if you're engineering a software system, for instance, at some point in the future. So hopefully we will try to see that the scope of this is broader, and circuits is really just an excuse to study systems. With that in mind, what will immediately start is looking at the basic concepts of voltage and current and things that relate to them, and then the core elements that form a circuit, and then how to put them together. And then the rest will be really different methods and tricks to give you more insight and ability to deal with larger and more complex systems. Let's go back here. So ELEC 201, Circuit Analysis 1. I'd like to, a lot of today will be casual, and some of the things that we talk about are not necessarily, what you saw on that list, part of the formal curriculum. But I want to make some connections. I'd like to make some connections between what we discuss here and what's happening in the world of technology and what the basic connections to science are. How many of you have looked at the image of a microchip under an electron microscope? Maybe not directly, but online, let's say. A photo of, OK. So I was trying to find some nice ones, and I found a couple of examples here. So this is actually under a regular microscope, I think. This is a photo of the Intel 486. You guys are too young to have had that computer, but I had that, and it was not my first computer either. So anyway, it looks nice and shiny and colorful. And if you scroll down on this page, this is, I think, from the University of Rochester, you will see some images, some SEM images. SEM stands for Scanning Electron Microscope. You'll see some SEM images of, for instance, in this case, wire leads, metals and so on that you have on these chips. And here you get a sense of the scale. The scale bar is 10 microns. So the width of these wires is maybe 3 microns. Now, this is old technology, right? How big is a micron, by the way? So a millimeter is 1,000 times smaller than a meter, right? What is the relationship between a micron and a millimeter? 1,000 times smaller. So a micron is 1,000 times smaller than a millimeter. So that's 1,000,000 times smaller than a meter. What's the thickness of human hair? How much? 5, 10? That would be very thin hair. I think it's more like 50 to 100 microns, depending. So you get a sense of the scale there, right? Now, like I said, this is old technology. What do you think the size of the feature sizes are on today's chip, on the, I don't know, I Core 7 or 9? What are the small feature size that the patterns on your integrated circuits have? But don't worry about being wrong. I want to make sure we're all awake. So what node are we at? Has anyone heard, as computer engineers, you might have heard of this concept node. They talk about a technology node from the semiconductors roadmap. I actually don't know formally what node is your latest product right now. But I'll tell you this. We are roughly in the 10 nanometer scale. Feature sizes that are 10 nanometers. So the size of your transistors and so on. Maybe a little less, maybe a little more. And that's why you can pack so much computing power in a small chip. Okay. So there is another interesting link here. This is a YouTube video. So this is the i7-8700K, a scanning electron microscope footage. So let's look at a couple of different parts of this. I want to mute the. So let me see if I can find some of the more interesting looking parts. Now this, by the way, is how many people have seen this? This is or something similar to it. Yeah, okay, so this is a bug in a scanning electron microscope. Images like this made the microscope very popular 50 years ago. But here is where you start looking inside a microchip. And this, I would think, is a cross-section of the chip. And you see all these different layers of wires going over each other and crisscrossing and all that. So it's really a fascinating world. It's like a gigantic city if you zoom in there. And so I want to show you a few different pieces of this footage. I don't want to go through the whole 10 minutes. But there's another image of the chip, I guess. Things like this. So if you zoom into a microchip, you will see a beautiful world of things that look like buildings and roads and all that. And you've got billions and billions of structures like this. So I hope you'll find this beautiful enough to go spend a few minutes, look up, and find some nice images and hopefully find some inspiration in that. This is the physical world. This is the physical layer. This is what's actually fabricated in Intel's clean room. Okay, and you see those people in bunny suits going and fabricating things. That's what comes out. If you take a step back and you try to now go to a level of abstraction, say, well, you know, who designs this? Well, a computer architect will design this a circuit like that, right? So many of you have had this course with Tor Amat, I think maybe last term, right? CPEN 211, I think. So Tor is a computer architect. So he would be the kind of person who designs the architecture of a circuit like this. And in that course, you dealt with things at a logic level, right? Zeros and ones, basically that level of abstraction. But you didn't really care too much about the exact values of voltages and currents running through that, right? There is then another layer of abstraction, if you want, which is really the circuits themselves. What the devices are, what the exact pieces are that go into this puzzle. How would you build an AND gate, for instance, or an OR gate that you would then use to build a logic circuit? And when you get to that level, you really need to understand the characteristics of those devices. Transistors, diodes, resistors, and so on. And in fact, if you look at people like me, I'm on that end of the spectrum where I work on designing and making devices like that, individual devices, that would then go to a circuit. So the circuit level of abstraction sits somewhere in this hierarchy, going from the device to the sort of Boolean algebra abstraction, and then eventually designing a computer architecture, and then sending it to a fabrication facility and having it come out like these images that you saw. So I want to start maybe by just looking at one example of the kind of circuits that we'll hopefully learn to analyze and study. And this is not something that you're expected to learn today and finish everything. This is going to come gradually. But I want to show you a little bit of the end story. Okay? So let's consider this circuit. I'll draw something and see if you guys recognize it. Is this starting to look familiar? Make a guess. Oh, good, good. Someone said NAND, yeah. So let's see if I can finish the circuit. So let's connect this here. So this would be one of my inputs. This would be the other input. That's also connected here. and this would be my output. Okay, so let's call this, A, B, and out. Okay. So I believe in your previous course, you really looked at these transistors as switches, right? NMOS and PMOS. And you said, depending on what you put here, 0 or 1, you would have these switches on or off, and you would get the kind of operation you want, right? Does that ring a bell? Everything? Even if you don't remember how it worked, that's fine. But I want to make sure that I'm connecting to where you left things off. So the point is, that's a very abstract way of looking at it. But in reality, these are transistors made out of flesh and blood, or those wires and pieces of material that you saw in the electron microscope. And these zeros and ones are voltage signals. So you would apply maybe 2 volts here, and you would expect here to go between 0 and 2. And to be able to fully understand the circuit and make sure that it works properly, you have to basically go through a full analysis of finding out what each voltage is everywhere in the circuit and what each current is flowing through every branch of the circuit. Okay? Here's another example. Let me see if I can think of right here. Let's see if this says something to you. What does this do? Again, let's say input and output. Anyone recognizes these shapes? Yes? What are they? They are transistors too. So the first example, we had these FETs. What does that stand for? Anyone know? Field effect transistors. And these are bipolar junction transistors. These were older circuits that used BJTs. And the other things I think you've seen, resistors. And if I have done this correctly, and you can verify later, maybe at the end of the course to see if I did this correctly, this should also perform an AND function. Okay? Now, I can, again, make a sort of similar level of abstraction to what you did in Thor's class for this and tell you how this works. But our purpose is to make this a lot more quantitative and a lot more analytical than a 0 and 1. So to do this, I want to basically establish a few rules that govern all circuits, be it like that or like this, regardless of the type of transistor you put in, the value of resistors and capacitors and what have you, things that are extremely general so that you can apply them to any circuit. Okay? And once you become familiar with that tool set, then you should not have to wonder about how to solve a specific circuit, because the approach to solving them will be the same for all of them. Okay? Again, feel free to interrupt me at any point. Okay? So I want to start by, first of all, making a very broad claim that electrical circuits, first of all, are not limited to things that you draw as wires and resistors and capacitors, things like that. In a very broad and fundamental sense, you might say, now I say this with hesitation, especially if this is going to be recorded, because many people are going to comment and object to this. But you might say everything is, in some sense, an electrical circuit. What do I mean by that? Think about the everyday phenomena that you see. mechanical forces, light, electromagnetism, of course, heat, you name it, whatever we experience in daily life. One way or the other, these are all governed by the interaction of electrons with atomic nuclei and electrons amongst themselves. Chemistry, for instance, you might remember from high school, is all about how these different electrons pair up, form bonds, and how you break one bond and form another, and how some energy is released. Mechanical forces come from the binding of different atoms together, or other types of glues, if you want, at the atomic scale that have to do with the interaction of electrons. Light is a phenomenon that has fully to do with electrons and their interactions. And you will see, for instance, that if an atom absorbs light, it means an electron in that atom is absorbing that energy, or a collection of electrons in a material are absorbing the energy that the light brings in. Thermal phenomena, you see that the thermal conductivity of a material has to do with either how electrons flow through it, or how this other particle called phonon flows through it. But phonons themselves come from atomic bonding that comes from electrons. So electricity and electrons are sort of at the foundation of a great deal of what we see in the world. And so in that broad sense, you might say, well, all these things are little electrical circuits. Okay, but maybe that's too broad a generalization. The science that goes into studying those interactions and being able to make fully observable predictions based on them, what's the name of that science? Does anyone know? I'm sure you've heard it. You hear a lot the word these days. It's quantum mechanics. Okay, you hear a lot about quantum computing, I'm sure, being in Vancouver and in computing. So quantum mechanics is the science that basically tells you how these things work. And it gives you all the properties of the materials. If you wonder why something is a metal, conducts electricity, and why something is a semiconductor, sometimes conducts electricity and sometimes it doesn't, depending on what you do to it, or why something is an insulator, you can, in fact, get a very a surprisingly complete basic understanding of it in a matter of 20, 30 hours of studying quantum mechanics. Building everything up from a second-order linear differential equation called the Schrödinger equation. And that's something we do, for instance, in one of our fourth-year courses here. So there is a very, very intimate connection between quantum mechanics and material properties, and ultimately all these elements that go into circuits: resistors, capacitors, transistors, what have you. In fact, do you guys know when the transistor was invented? Does anyone know? When was the transistor invented? What's the official word anyway? Earlier than the 70s. So 70, but that's a good start. Go back a little. Late 40s. Okay. When did the electronics industry start? Even I'm too young for that. So Fairchild was an early company, for sure, but the electronics industry itself is more than a century old now. You probably heard vacuum. Anyone who plays guitar here who has a fancy vacuum tube amplifier? No? I hear some people still like vacuum tube amplifiers. So vacuum tubes were invented in 1904, I think, 1906. Their solid-state counterpart, which is the transistor as we know it, took another 4 or 5 decades. Now, I'm not a historian of science, but it doesn't take a whole lot to notice that it was the time that it took quantum mechanics to develop and solid state physics so that people understood how materials work to be able to make electronic components and devices based on quantum mechanics. And that took a few decades. So quantum mechanics is sort of a big part of the story. Another big part of the story, of course, is electricity and magnetism, electromagnetism. And that's a science that, of course, has been around for much longer. And there's a very intimate connection. Again, I suspect in your first year physics, you've seen examples of how you have charge somewhere and you establish an electric field, how you have a current and that leads to a magnetic field. Any of these ring a bell? Yeah? I'm not suggesting that you should like them, but trying to make the connections. So there is all those connections. But as far as solving these circuits go, see how we are doing time-wise. Because we'll take a 5-10 minute break in the middle of the 2 hour. So as far as our topic goes, all the science of electromagnetism and quantum mechanics get condensed and lumped into a few properties. And basically, electromagnetism tells us what we call the rules of circuits. And there are really only 2 rules. And we'll talk about them today. One is Kirchhoff's current law, KCL. One is Kirchhoff's voltage law, KVL. Okay? That's all you need from electromagnetism for this course. From quantum mechanics, all you need is how each element works. The output of all that science has led to an understanding of how a resistor works, how a transistor works, in fact, how a wire works, and all of that. So if we understand from a circuit level point of view how each of these elements work, we've basically done all the quantum mechanics needed for this course. Okay? So, and we won't go into, of course, quantum mechanics or electromagnetism. That's the topics of other courses. But it's really the amalgamation of those 2 branches of science that come together and allow us to study circuits. Okay? So with that, we are going to now start talking about circuits at the level that really concerns us. Any questions, comments? Any interesting point that comes to your mind that I might have missed, that others might find useful, interesting? So I want to start by talking about circuit elements, the components that we'll be working with. Some of them you might call devices or circuit elements. What would you say is the most important component in a circuit? A wire. Yeah, absolutely. I mean, now you might say a wire is a form of resistor with 0 resistance. But really, yeah, a wire. So now, it's surprising how much misunderstanding happens when we deal with wires in circuits. So it's something that that requires really special attention. I think, in fact, it's the most poorly understood element. Okay. Now, what is a wire? An ideal wire, something that we use as a simplification to represent pieces of conductors with almost no resistance to the flow of electric charge. At the circuit level, an ideal wire has 2 properties. One, well, does anyone want to take a guess as to what the properties of a wire are for a circuit level understanding?
There's no voltage drop across it.
One, there is no voltage drop across it. Now, voltage is a very subtle concept, and we'll talk about that in a bit. But it's the same thing basically that you've seen as electric potential in basic electricity and magnetism. If you look at a wire, an ideal wire, no matter how long it is, there's no potential drop along the wire. The electric potential is the same here as it is here, as it is there, as it is 100,000 kilometers away. So there's no potential or voltage drop. And we kind of use the word voltage and potential interchangeably. But in this course, we'll gradually use voltage more and more. So there's no voltage drop across a wire or along a wire. What's the other property? It's actually, in a way, implied in the first property. There's no voltage drop no matter what current is going through the wire. So a wire can actually allow any current. An ideal wire. Again, of course, don't take these things too literally and say, I'll go take a thin wire and plug it somewhere and expect 500 amps to go through it, and you will cause a fire. So an ideal wire. At our level of abstraction, the line that you see connecting those transistors will allow the passage of any current, any level of current, however many amps you want, without any voltage drop. Okay? So here for now, I'll say ideal components. And ideal as in a simplified idealistic picture of these components. Right? So a wire or allows the passage of any level of current and has no voltage drop along it. Okay. Now we'll soon see this in examples. Let's think of another element. What is a switch? What is a switch?
It's actually something that acts either like a wire or a complete break in the circuit, or a resistor of infinite resistance.
Yeah. So it's like a piece of wire that you put in there, and if you disconnect the switch, it means you've taken the wire away. There's nothing. Okay. So switch, if it's on, it's a wire, which means allows the passage of any amount of current and has no voltage drop along it. If it's off, it means there is nothing there, no connection there. What is a resistor? Yes. Do you mind speaking up? So a resistor, that's a good answer, is a component over which there is a potential drop. But can we maybe be a little more quantitative? What determines that potential drop?
Are we talking about ohmic resistors or just resistors?
A very simple ohmic resistor. That's a very good question.
Potential drop proportional to the current.
A resistor is an element it has two ends, like a wire. It's an element, the potential drop across which is proportional to the current through it. Okay? This is something you might have seen in the past as Ohm's law. Does anyone remember Ohm's law? Yeah? So people make a big deal out of this. Ohm said in a resistor, V equals Ri. Well, it's kind of the definition of a linear resistor. Now, you can actually arrive at Ohm's law if you start from quantum mechanics and do all those things. But so presumably Ohm made this observation that there's this great class of materials, conductors, over a very broad voltage and current range. They behave essentially as a multiplier. If you feed a current through them, they will just multiply that by a factor of proportionality and give you a voltage across them. So a resistor is an element that has its voltage proportional to its current. Now, we are already starting to talk about proportionality. That means a simple equation. And we have to be a little more explicit there. OK, so I'll draw an element and formally define a voltage and current for it. So this is an element. It's not necessarily a resistor. It could be a resistor. But what's important here is that it has two ports. Okay, entrance, exit. So there is basically a wire going from one side and coming out the other. We have to define a voltage and current. Now, voltage and current turn out to be algebraic quantities. They can be positive or negative. They have a sense of direction associated with them. So we'll define them like this. V representing voltage and I representing current. So a resistor is an element in which V is proportional to I. And that constant of proportionality is called resistance. Okay. Now, what is current, by the way? What is the definition of current? Does anyone know? So let's make an analogy. If we thought about water flowing in a river, and I asked you to measure the flow rate of water in the river, what would the unit be of the flow rate? Yes. So let's make that connection. Yeah, but that's correct. So in a river, if I say, measure the flow rate of water in the river, you would give me a number. What would the unit of that number be? Right? So volume per unit time. So it would be something like meter cube per second or liters per minute or something like that. So an amount of material. You could even equivalently maybe talk about weight. You could say, how many kilograms of water are flowing per unit time through every cross section of the river. There is the same picture applies in the flow of electric charge. So you have these charged particles inside materials, and they're moving. And now the unit of charge is coulomb. So you say we have 1 coulomb of charge, or a microcoulomb of charge, or a nanocoulomb, or what have you. How many coulombs per unit time go through a cross section of your wire or your resistor is the current. So current is the rate of passage of charge, and its unit is coulombs per second in the international system. And there's a name for that. amps, right? Amperes. So the unit of current is amps. Now, when you talk about flow, I think then you would immediately appreciate the fact that there is a direction associated with flow. If things are going through the riverbed, then they're going this way or that way. And that's why when we indicate a current, we always assign a direction to it. Now, here is an extremely important point that I'll be making many times during the term. And I ask you guys to keep reminding yourselves of. I'll make this point and we'll take a break. I've shown the current with this arrow going from left to right. That does not mean that the current in the circuit is going from left to right. Okay? This is not a complicated point, but it's something about the human brain that we encounter great difficulty in accepting that if I've drawn an arrow like this, that the current might be going the other way. Can someone shed light on what I mean? Why is it that I say if I've drawn it like this, it does not necessarily mean that the current is going from left to right? Yes? It could come up negative. Like I said, a current is a quantity that can be positive or negative. What this means, this is a convention. It means that if I do everything and solve my circuit and get a value for this current I, if that value is positive, the current is in this direction. If the value is negative, it's actually in the other direction. Because logically, if I say something is going from left to right with a quantity of -3 amps, it really means it's going from right to left with a value of 3 amps, right? It's like saying the river is flowing this way with 3 liters per second of flow rate, but I say no, it's flowing the other way with -3 liters per second. Okay. Because it's a quantity that can be in either direction, we have to pick a convention, assign some direction, and be fully prepared that the value of the quantity might be negative, in which case the current is actually the other way. Okay? And we'll know that after we solve the circuit. So very, very important point number one, that when you see something like this, do not assume that that's the actual direction of current flow in the circuit. Okay? I think it's a good point to take a 5-minute break. So and by the way, I want to remind you, today we are sort of jumping a little bit here and there. I'm trying to get to the end product of the course today, so to sort of just establish a general intuition. We'll go through these, of course, in a lot more detail and formally. I have the whole term for that. But let's see how far we can get today in being able to finish the course. Okay. So the current. So to understand the resistor, and in fact, to understand the wire even, we needed the current, right? So current flow rate of charge, and charge being measured in Coulomb, current then would be in coulombs per second, which is known as amp. And we saw that it could be positive or negative, meaning that it could flow in one way or the other. What about voltage? What is the definition of voltage or electric potential? Can anyone think of an analogy that describes electric potential? I always find it a little harder to imagine than current. Current is easier to visualize. You say these charged particles that are moving.
Well, an analogy would be continuing on difference in height from the start of where it's flowing to where it ends up.
Yeah, thank you. Yeah, so the water flow analogy works again somewhat. It's imagine a river. Well, if the whole surface of the riverbed was flat, you wouldn't expect a flow one way or the other, right? You would have a pond, not a river. You need a little bit of a height difference, and that's the voltage across an element in analogy. That height difference in a gravitational field means a force, a gravitational force that drives water from one end to the other, right? In an electric field, that height difference, it's not physical height. It's an abstract equivalent to a height. It's called electric potential. It's the same thing that you've seen in your first year physics, so nothing new there. Electric potential. And I think we could all appreciate the fact that when we talk about the height of a point on the surface of the planet, for many purposes, it's the height difference between 2 points that matters. So, for example, in the river, it's really whether one end is higher than the other. If you have a flat river on top of Mount Everest, it's still flat and there's no water flow. It's a water pool, not a river. So it's height difference that matters. Voltage, the voltage of an element that we define like this in a circuit, is that the equivalent of that height difference, but the electric equivalent of that. So it's what provides the stimulus for the flow of current, if you want. So I'll write this down. Voltage is the potential difference between the two ends of an element, okay, or between 2 points in a circuit. So electric potential difference between 2 points. And if you think about that height analogy, I think you would agree that, again, if I say there is, between points A and B, there is a 5-meter height difference. Is point A higher than B or B higher than A? I have to specify, right? Can't guess. So that's why voltage also has a sense of direction or polarity, you might call it, to it. It's a difference, and so you have to specify if this side is higher than that or that side is higher than this. And like current, it can be a positive or negative value. So I want to issue the sort of second important reminder here. When you see something like this, where I have said V, and it has a plus side and a minus side, a positive side and a negative side, it does not, okay, it does not mean that the left side is necessarily higher in potential than the right side. If V is a positive number, sure, that's what it means. So if V was 3 volts, then yeah, that means that the left side is 3 volts higher than the right side. If V was minus 3 volts, then that would mean that the left side is lower than the right side. So both current and voltage can be positive and negative. And the unit of V is volts. This is capital V. And if you define a reference point, then you can measure all heights with respect to it. So you can say, yeah, sea level is my reference, and the height of Mount Everest is, let's say, 8,000 meters to make things simpler, and give me the height of another mountain. You know, I know what's the height of Black Tusk. Anyway, let's imagine some mountain which has a height of 1,000 meters. Then the height difference between Mount Everest and that imaginary mountain would be 7,000 meters, right? One is at 1,000, the other is at 8,000, and the difference is 7,000. You have the same exact situation in a circuit. At some point, a little later on, we will use this, develop this method called nodal analysis, in which we use node voltages. And some of you might have seen that in the past. There, it becomes really important to specify a reference. For now, it may not be as important to have an explicit reference. What will ultimately matter in the circuit is the differences between different points. But a reference is a useful point that at some point we'll define. Okay? So anyway, this is voltage and current, and a resistance is simply an element that follows this very broad observation, which is many materials, if you cut out a chunk of them, a regular conductor, if you cut out a chunk and you apply a voltage through it, across it, you will measure a current through it. And if you double the voltage, the current will double. If you triple the voltage, the current will triple, because they are proportional. And this proportionality is called Ohm's law. Okay. And the factor of proportionality is called resistance, and it's measured in units of ohm. Now, the specific element known as the resistor can be more explicitly shown as with this shape, with R. So you would say this is I through it, this is V across it, and R is the value of the resistance. Question: can resistance be negative? Who says yes? Who says no? Okay. Too many lights in my eyes, it's hard to tell. You guys can do whatever you want, I won't see anyway. So, someone said yes. Can you elaborate on that? I think you said yes. Right?
Yeah, I think that there can be like active elements that have like negative.
So that's a very good and very sophisticated and advanced answer. So we have an answer here that there, in fact, you can have at least what you would call negative differential resistance, which is situations where you see an increase in voltage associated with a decrease in current, or vice versa, right? And that's true. But let's go back to our simple resistor like this. So no sophisticated piece of material or device. In this context, can I have negative resistance? The answer is yes, actually. Now, I'm saying that with the hope that I won't confuse you with it, but there's a little bit of fun here. The answer is yes, as long as you remember that you defined your resistance as negative. What do I mean by that? In this kind of resistor, really, what you have in your lab kits, those resistors, 5K, 10K, and so on, they are not negative resistors. But what does positive or negative mean? It's all a convention. So imagine I drew a resistor like this, and I said this is 5 ohms. This is the symbol for resistance. I think you probably have seen it before. 5 ohms. And if I define this current and this voltage for it, I have Ohm's law, V equals 5 times I, right? From a mathematical or algebra, from the point of view of the algebra of the problem, I could just as well have defined this other problem. I could have said, no, I call it minus 5 ohms. And I say, I want you guys to take a moment to look at what I've done there, to see whether these two pictures are completely equivalent or not. Any thoughts about whether these are equivalent?
Would it be a reasonable way to think about it like this, that instead of resisting the flow of the current, the negative resistor is helping the flow of the current so it can flow from a lower to a higher?
See, so we have a suggestion here that a negative resistance, instead of resisting the flow of current, is helping it. Right? And that, again, would be a very sophisticated device that perhaps could do that, right? What I'm really talking about here is not that. That's a valid viewpoint for a certain category of devices. But this, what I'm showing you here, is not that. Yes?
Is it the direction of the current?
If you see, well, in this case, I chose to reverse the direction of the voltage. I could have just as well done the direction of the current. Look at this. So let's take the upper circuit. In the top circuit, if I say my current is 2 amps, what's the voltage in that circuit? 10 volts. So let's write that down as an example. So an example would be, I have the 5 ohm resistor. I have a 2 amps current. My voltage from Ohm's law is 10 volts. In the bottom circuit, if I have I equal 2 amps again, what will my voltage be? So I have this minus 5 ohm. I have 2 amps. Have fun. What is it? Signals? What's the voltage? Look at the equation. So current is 2 amps. What's the voltage? Minus 10 volts. Now, what is the polarity of my voltage? This is how I've defined it. So minus, plus. And the value is negative 10 volts. Okay? So if I say, go back to the convention that we were talking about 10 minutes ago, right? If I say that my voltage is minus 10 volts, and the way I have defined the polarity, well, this side is, has the plus, and this side has the minus. Meaning, if V was a positive number, this side was higher than that side. But V is a negative number, so it really means that side is higher than this side. So this is completely equivalent to this. Okay? This is an example of the kind of things that one can get confused about quite easily. So these two pictures are mathematically equivalent. And if you really wanted to confuse yourself, you could use negative values of resistance. And you could even play with a circuit and choose to give negative values to some of the resistors. But remember that that your sign convention for the voltage should change. Or if you really wanted to completely confuse yourself, you could do, in some cases, you could reverse your voltage. In some cases, you could reverse the current. As long as you stay consistent with the way you write Ohm's law, with all these plus and minus signs, and the other circuit laws, you will get the physical answer correctly. It's not a problem. But of course, that's not a wise thing to do, right? So this is a bad idea. It's correct, but not a good idea. Okay. So with this in mind, we will say that the kind of resistors that we work with, the elements that we deal with in our lab and in the circuits that we design and solve, they are positive. Okay? Knowing that mathematically, we could always, it's a bunch of equations, right? You could always throw in a negative sign on the two sides of the equation, as long as you remember what you've done and stay consistent, right? But of course, you don't as an engineer, you don't want to do that unnecessarily. Okay? So correct, but not a good idea. Okay. All right, so here's, we've been having a little fun with resistors. I want to introduce the next element. And again, don't feel like you have to really fully understand and be able to apply all these in after 1 hour of lecture. We'll do a lot more of this over the coming days, and much more systematically so. But we're trying to get to the end now. I'll throw in one more element for now, a capacitor. Again, it's an element that you can specify like this with a current, and voltage. What's the definition of a capacitor? Well, give me a qualitative definition, sort of a gut feeling. What does a capacitor do? Stores charge. Very good, right? So it's like going back to the water analogy. It's like a reservoir. You put so many liters of water in a tank. So you put so much charge in a capacitor. 5 coulombs of charge in a capacitor, for instance. Okay. From a circuit level point of view, the definition of a resistor was V equals Ri, right? Ohm's law, just definition. An element that behaves like that, which happens to be a very broad range of conductors, V equals Ri. A capacitor, in its simplest form, is 2 pieces of metal, two plates that you put in parallel, and you have a wire connected to each of them. From a circuit level point of view, relating its voltage and current, does anyone know the definition of a capacitor? I appreciate where the exponential connection comes from, and we will see that. So that's a very good connection there. But it's the exponential you will see is a consequence of putting a capacitor in a circuit. But a capacitor, isolated capacitor, that we want to understand. And by definition, I mean a relationship between its voltage and current. The same way we had the relationship between the voltage and current for a resistor, V equals Ri. I want something similar for a capacitor. And so it's an element again, but specifically, if I wanted to show its own specific symbol, it would be like this. And you would say it has a capacitance C, and again, a voltage and current. Can anyone think of a relationship between voltage and current? Very good. So let's do that. Before we get a connection between voltage and current, let's see if this rings a bell. For a capacitor, if you say Q is charge in Coulomb, the amount of charge stored on its plate. And the way it works is if you have negative 5 coulombs on one side, it means you have positive 5 coulombs on the other side. Does this look familiar? Q equals CV for a capacitor? That's in fact the sort of basic definition of the value of capacitance, C. The amount of charge that you put on the plates is proportional to the voltage developed between the two plates. Or you could say, the voltage that you apply to a capacitor will lead to a proportional amount of charge on its plates. But in circuits, we are normally more concerned with currents and not charges. So then from here, what would the definition of a capacitor be in terms of relating its voltage and current? Can you guys take a minute to work that out on your own? Feel free to consult others, of course. So the question is, from this, can I obtain a relationship between I and V? Starting from the relationship between Q and V, can I obtain a relationship between I and V? You want to? Yeah? Yeah, and that's it. You take the derivative. So let's see. We said current is flow of charge. How many coulombs per second go through a point in the circuit, right? When you start charging a capacitor, you're putting a current into it, and it's this current that brings the charge, that charges up the capacitor. So if it took 5 seconds to charge the capacitor to 5 coulombs, what was the amount of current? If it took me 5 seconds to deliver 5 coulomb of charge, it was 5 coulomb per 5 seconds, right? So that's 1 amp. So current is really charge by time. But you have to be careful, because in a circuit, these things could change with time. If you have a circuit in which things are not settled and constant, the value of current could change from 1 second to the other. So you can't just take the entire charge and divide it by the entire time. You have to do it locally in time. And that's what takes you from this to differences and eventually differentiation. Right? So derivative. So it's really dq by dt. And in fact, that's the formal definition of current. Flow of charge in time. That's what we were talking about. Mathematically, this is how it's represented. And if you take that derivative, d of CV by dt, assuming that the capacitor, the value of C does not change with time, so that you can bring it out. Then you get C dV by dt. You will just pull C out of the derivative, and you get C dV by dt. So as far as circuits are concerned, let's just write it in compact form. I equals C dV by dt. It's very similar to Ohm's law. There you had a proportionality between current and voltage. Here you have a proportionality between current and not the voltage itself, but the derivative, the time derivative, the first time derivative of voltage. And here's where you see why I say it's important to be fluent in derivation or taking derivatives. Well, derivation, of course, but in differentiation and taking derivatives, and by extension, integration as well, because it's the reverse process. Did anyone see something like this in first year physics? Yeah? Okay. So, and the rest might have seen it, but don't remember it. And that's why today and next time we'll review these in a lot more detail. Does anyone now remember what an inductor looked like from the circuit level point of view? Yeah. So in a capacitor, the current is proportional to the first time derivative of voltage. In an inductor, the voltage is proportional to the first time derivative of current. And it's amazing how much richness these two simple elements can bring to circuits. You can do really a great many things with them. We will see this in a few weeks, but I hope you can at least sort of sense it at a very, very abstract, basic level, that if I had a circuit in which I threw in some resistors and capacitors, that the equations of that circuit would not be simple algebraic equations. They would be differential equations, because they would have some derivatives. I think you guys are taking differential equations this term. Yeah, so it's as we go along, by the time we need them, hopefully you'll have seen more. And so you'll be ready for that. We don't need a whole lot of differential equations, okay? We just need a couple of different forms, and that can do a lot for us. By extension, I hope you also can imagine that if I threw in not just a capacitor and a resistor, but also an inductor in the circuit, now I have some voltages that are proportional to some currents, some voltages that are the derivatives of some currents, and some currents themselves that are the derivatives of some other voltages. And so if you solve the circuit equations, you will end up with a second order differential equation, which again we'll see in a few weeks. So it will have second derivatives. Okay. Solving those will not be anything special to circuits. Will be exactly what you see in your differential equations. Now, I don't want to go through all of that, of course, in one lecture. Again, this is I'm trying to get as close to the end as possible, just to show you the overarching theme. What I want to do, and maybe we'll take a pause if there are any questions. And by the way, I might forget to ask frequently if you have questions, but feel free to interrupt. There's nothing here that, that needs me to speak uninterrupted. Okay. In fact, it would be very helpful if you could interrupt and ask questions. I'm sure if you have a question, chances are at least 20 other people have the same question. No, it might be something that I haven't thought about. Okay. If none at this point, I want to switch gears a little bit. So far, we've been talking about these elements in isolation: a resistor, a wire, a switch, a capacitor. You haven't connected them anywhere. Okay. Once you connect them, it's like now you're sending cars on the road. You need some rules for the traffic to work. And so for a circuit to work, we've learned from nature that there are two rules that it follows. And they are amazingly general and powerful. And those are Kirchhoff's voltage and current laws. So I want to talk about those for a few minutes. Sorry. So the topic is really how to put things together in a circuit and analyze it. And for that, we need I hope I'm spelling this correctly, Kirchhoff's voltage law and current law. KVL and KCL. Now, by the time I tell you about them, you will wish that you were born before Kirchhoff, because you will be like, oh, I could have said that, and your name would be associated with it. So sometimes there is an advantage in being born earlier. Let's look at KVL first. So I will draw a circuit, and I'm not even specifying what the elements are. Could be a resistor, a switch, a capacitor, what have you. I have some wires, of course. Okay. This is an example of a circuit. So this is an example. In order to be able to talk about this quantitatively in mathematical language, I have to specify variables, voltages and currents for each element. So if you call these elements 1, 2, 3, 4, 5, again, can be anything. So let's call this V1, I1, V2, I2, V3, I3, this would be I4, V4, I5, V5. And you'll notice that I wasn't particularly concerned with which directions to choose with the voltages and currents. I went quickly and did what I wanted. I assigned whatever polarities I wanted, knowing full well that these are quantities that can be positive or negative. If they come out negative, it means they were the other direction. No big deal. I don't have to worry about it ahead of time. Kirchhoff's voltage law, if I write it like this, I'll write a very loose definition, and if I write it like that, you'll be like, oh, there's nothing in there. What's this? Voltage is a well-defined quantity. That's really all there is to it. What do I mean by that? let's take element number 1. I said the voltage across it is V1. And this is how I chose to indicate the polarity, meaning that if V1 is a positive number, indeed, it means that this side is higher in potential than this side. And if V1 was negative, then it was the other way. But remember, we said V1 is basically the difference in electric potential between these 2 points. And you could choose a reference potential somewhere else. Very often, later on, you will see that we call that the ground, and we assign a value of 0 to it. But for now, we don't care. A reference potential somewhere else with respect to which you're measuring this and that, and then the difference becomes V1. So you would have a potential here with respect to some reference, and another potential here with respect to some reference, and then another potential here with respect to some reference, and another potential here with respect to some reference. KVL is saying that these are well-defined quantities, in that if you start from one point and go around the circuit and come back to that same point, you have to obtain the same value. Otherwise, it would not be well-defined. So this is well-defined and useful. Imagine, let's give these points names. A, B, C, D. Assume that point A has an electric potential of, let's call it V sub A. Okay? What is the potential at point B? If the potential at point A is V sub A, or the height of point A is V sub A, what's the height of point B, according to my notation? Your guess is right. So if this is at height V sub A, and the difference between this and that is V1, what's the value of that? Remember, V1 is the difference between the height at point B and A, right? That's the difference. So by that same approach, what's the potential at point C? So let's see. The way I have written it, V2 is the difference, VB minus VC, right? So VC is VB minus V2, which then, if I replace from the first line, is VA plus V1 minus V2. Now, if I want to go through element number 3 to go back to point A, what's the relationship between VA and VC? Again, this V3 is just the difference between those two. the way I have indicated it, is VC minus VA. So VA is VC minus V3, which I can then replace from the second line and get is VA plus V1 minus V2 minus V3. So look at this last equation. I'll just repeat it here. I'm saying VA equals VA plus V1 minus V2 minus V3. So far, we haven't applied any rule other than the definition of potential difference and voltage. Okay? Kirchhoff says voltage is a well-defined quantity. This VA, there's actually a physical quantity there. So if you go around a loop like I did and come back to A, and you get something like this, this VA is well-defined. It's the same thing on both sides. So you can cross it out. So you'll get this. This is the more sophisticated, if you want, or mathematical expression of Kirchhoff's law that says the algebraic sum of voltages, or we should say voltage differences, around a loop is 0. Does anyone remember this from first year physics? Just going around the loop and yes, yes, yes. Yeah. So again, if you don't remember, it's fine. But what I'm hoping that you appreciate from this is that there's nothing in this other than acknowledging that voltage is a well-defined quantity at each point in the circuit. And there is a similar expression for Kirchhoff's current law. We are out of time, but I'll just say a couple of sentences, and then we'll continue next time. And this is what I want to say. If you write this KVL equation for every loop in the circuit, in this case, we have these two. And similarly, a KCL, a current law that relates these currents, if you do this, you will have enough equations to find all voltages and currents in the circuit, no matter how big the circuit is. And these equations will be algebraic equations if you have just resistors and sources. And if you have capacitors and inductors, they will be differential equations. But this is all the science that goes into this. The rest is practicing how to do those things. And so next time we will do this a lot more formally. Okay, thank you.